In the previous video I got as far as how to generate a listing file from the ROMs inside the zip30. I showed you a formatted file, but in reality what comes out of the decompiler is something more like this. It looks like garbage, but it's actually a series of instructions that the decompiler has made an attempt to construct from the raw data inside the firmware ROMs. The next step after this is to tidy it up a bit. So what I then end up with is something a bit more like this. It's not more readable in terms of the functions of the machine, it's just easier to read. And the task now is to get from something like this, which is just raw machine code in a list file, to something like this, which approximates the original source code, so that it can be read and I can fault find on the machine. Now it's quite a significant task to do that. It's not trivial. It took me about a month to do it on this machine. In the previous two videos I've given some sort of generic guidance on how to get the firmware out of any ROM and create a list file. You do of course need to know which particular processor you're dealing with. Now this machine has got a Motorola 6800, so all the discussions from this point on will be based around this processor. But in reality it doesn't really matter what processor you're using, as long as you understand what the instructions are that you're looking at on the analyzer screen. So obviously the first step is get a detailed instruction set for the processor that you are using. I mentioned in the previous videos that I'd created an address map for the ROMs. I've actually created an address map for all the hardware devices on the machine. As I'm sure you're aware, an embedded microprocessor system has an address map, and in that address map each device that can be addressed within the system has a specific address. Now I've added an extra column on this table from the one we looked at in the previous video. You can see that what we have now is an extra column, and this column represents the address of the individual ROMs within the address space. It's actually the address of the first byte within each ROM. This is the upper 8 bits of the 16-bit address bus, and if we look at the address in hex, for example ROM 5, we can see that it's at address 3000 hex, and then if you look at the address in binary you can see it's 0011 4 zeros. That's obviously then followed by another 8 zeros. If you do that conversion you'll find that those two are the same number. The way I determine the address is looking at the actual physical circuit. The ROMs are addressed through a buffer. The buffer only handles these 8 bits, and they are connected to the chip select pins of the individual ROMs. So all I did was to monitor the chip select pins of the ROMs and see what address range was present when the chip select was active, and that way you can see what particular ROM was being addressed. If you then capture the instruction at that particular address, you can look into the ROM and see where it is within the ROM. You can then work out essentially where that ROM fits within the address space and what its start address would be. These are 1K ROMs, so each ROM occupies 400 hex, and it was just a matter of figuring out where that first byte was in the first ROM, and then it was easy to calculate the remaining table. So once I had that, I could reverse compile the code I'd read from the ROMs, and then we ended up with the raw list file. The next step is to figure out where we're going to start, because obviously what we have once that's done is just a huge file that contains information like this, and obviously we need some way to start to interpret this, because not all of it is code. There are lookup tables, some of it is redundant, and the block right at the end of a file like this is just symbols, so it's not actually code at all. So to start, what you need to do is look at the spec sheet for the particular processor that you're going to use, or that is in the machine that you're working on. And so that's what I did here. For this particular processor, I wanted to find the program entry point. So in other words, I wanted to find the reset vector for the processor. That's the address the processor jumps to whenever it is reset. So this particular processor, which is the 6800, it has a set of reset vectors and interrupt handler vectors. So these are specific addresses that it will jump to for reset, or following a reset, and when an IRQ occurs. So in this case, the one we're interested in to start with is the reset vector, and we can see that is 3FFE. Now, we can't actually capture 3FFE because the analyzer needs 2 clock edges to capture any data. But if we look at the decompiler, we can see that it's saying that the reset vector will jump to 3A1C. That's typically how the reset vector table works. Whenever anything jumps to the reset vector table, an address is stored there that the processor will jump to whenever it ends up at one of the vector table addresses. So in this case, when the machine is reset, it will jump to 3FFE, and that will then jump to 3A1C. So we can test that by setting up an appropriate trigger. So if we go to the analyzer, I will set that particular address. So it is 3A1C. We go to waveform, I'll set it to run, and I will now reset the ZIP30, and you can see that once it's reset, it does indeed jump to that address. Ignore this error, that's, as I said, it's because there weren't enough clock edges for it to be fully confident it's got the right address. But we can see that initially we started off at FFE, and then there's nothing before that, that's where the data was being captured, and that caused it to jump to 3A1C, and that is the address entry point. So if we look at the decompiled data, I've commented this, and I started off here by commenting that this was the reset vector. These dashes here are where I've removed a large block of code. You can see there's a big jump between these two addresses. We'll look at this in another video, but in this section there was a large block of initialization code, and what that did was to initialize all the PIAs and the various parts of the system to make sure they all had the correct values at the start of the system boot up. But I've removed them from here because they weren't going to be part of the data I needed to trace through, and it was just making the documents bigger and more cumbersome to use, so I took that out. I've actually done that in a number of places where there are blocks of code that I wasn't interested in. I took them out of the document. They're obviously still in the ROM, but if I'm not jumping or going through them, there's no point having them in the document that I'm trying to use to fault find with. Okay, so that's how I determined the entry point of the program. Now, as I said, this was quite a big task and it took a long time, so I'm going to jump through most of it. If there are any specific parts of the process you want me to go over in more detail, then drop a comment and I'll include that in a future video. So once I had the program entry point, I wanted to see what the interrupt handler was taking care of. It's always worth doing that fairly early on in the process, because if the interrupt handler is handling a lot of different parts of the system, it can make it much more straightforward to do the debugging and the deconstructing of the firmware if you know exactly what the interrupt handler is handling. In this case it's actually a fairly simple interrupt handler, and we'll have a quick look at it now. But again, back to the vector table for the machine. So this is from the decompiled code again. I've commented it here, and from now on I'll show you the commented version of the document rather than the raw one. But bear in mind, this is the result of this work. Initially this is just all numbers, there's no comments on it whatsoever. But if we look at the reset vector, which is the last one, you can see that's where we determined the program entry point was, and now we're interested in the IRQ handler, and the interrupt vector is at 3FF8. So all that will happen if the system jumps to 3FF8 in response to an IRQ being triggered is it will then redirect the code to an address of 3FBD. So if we now try to trap 3FBD and trigger an interrupt, then we should see the machine stop, or at least the analyzer capture data at that point. So I'll go back to the trigger, and we'll now change from the reset vector, or the program entry point, to what should be the IRQ handler. So if I enter 3FBD, we'll go back to the waveform. The zip30 is running, so we'll set this. I'll press a key, and the first thing to note here, and this is something that is a real trap if you're not careful and you don't understand fully how to use these machines, is although we've captured some data here with the analyzer, in other words we've triggered the trigger event that we've set, it's incorrect. I've pressed the key in this case to capture this, and it's consistent, it will capture this every time when you press a key. But as it turns out, the keys are not handled by the interrupt controller. So if we look at the IRQ handler code itself, which is at 3FBD, we can see that what we should be getting in terms of the data from 3FBD is B68023. So 3FBD, we're seeing B63C2D, which is obviously incorrect. So that's not what we're expecting to see. What's actually happened here is this address has been triggered from here. And this is one of the problems you'll get if you're not fully familiar with how the processors work and the analyzer works. This is actually part of a subroutine, and this instruction, return from subroutine, causes the processor to jump from this address back to the calling function. And we can see that that's what's happening when we look back at the analyzer screen. So we can see we've got 3FBD, which is the start of the IRQ, but following that we've got some weird looking addresses, 01FD, 01FE, 01FF. Now if you know the 6800, you know that they are most likely to be the stack, and also because they are incrementing, you can be fairly certain that its values being taken off the stack. So in other words, what's happened here is we've actually been triggered by the overrun from this function running into the 3FBD address, and that's what's triggered the analyzer. But from what actually happened was from 3FBC the zip30 jumped back to a different address, and in jumping back and using a return from subroutine instruction, it pulled the return address off the stack. So in other words, we're actually up here and we're not down here as we want it to be. So that's just because it's the way that the processor works. It when it does a jump, it does tend to fetch the next instruction address, and that's just for streamlining and efficiency within the processor. It's basically doing a lookup of the address it thinks it's going to need next. In this case it's wrong, it doesn't need to look at 3FBD, and in fact when it fetches the data from the stack it will jump back to whatever address was stored on the stack by the calling function. So what we need to do is to be able to trap on the entry to the IRQ handler, And the easiest way to do that is to just change the trigger address from 3FBD to 3FBE, and that will not be hit by this function. It will only be hit when we actually do come into the IRQ handler. So if we change the trigger address to 3FBE, and then go back to the waveform, select run, I'll press the same key again that I did before. If you remember previously, that caused the interrupt handler to be triggered. In this case it hasn't. As it turns out, the only thing that actually triggers the interrupt handler is the tape reader. So if I now press a button on the tape reader to read a character, you can see that we've triggered the interrupt. So we're now in the interrupt, and what we can do, as I said in the previous video, is use this almost like we're single stepping through the code. So what we're expecting to see now is the B68023, and that is exactly what we're seeing, B68023. But more importantly, we can now go through and we can see if this branch occurs. So do we end up at 3FCB? So as we go through, we can see that we don't branch, we carry on executing the code through the handler, and the bit we're interested in is reading the data port. Now again, these are labels I've given to certain addresses, and in this case it's the PIA 11 port B data, which is the reader data input, and I'll go over in another video how I determine that. But what we're looking for is this particular address. You can see what the address is if you look over here. It's address 80. So if we keep scrolling across, you can see address 80, so we're going to read address 80. That's followed by 22, which is part of the same instruction, and we're going to store that value in a buffer. And again, I've given a name to a buffer. I determined this was what it was by this action. So by reading the port that was connected to the reader, I could determine that what it was doing was using this address as a data buffer for that data. That's at address 53. So we need to look for address 53, which is here. We can now see that what we have along the top, 3FC5, 3FC6, is this particular address, which is the store address. In other words, store the value at address 53, and the value is then the data value that follows, and in this case it's 41. So you can see we have a data value from the reader of 41. If I just now reset the trigger and press the key on the tape reader to read the next data byte, you can now see we have an address, data value of 43. So in other words, what this is now doing in the IRQ is we are just reading the value from the PIA that takes the data from the tape reader. That's all the IRQ actually does. So what you can do once you determine this is obviously comment the code. So that's what I've done here. It then actually moves on to increment a sprocket hole flag. That's just telling the system that it's hit the next sprocket hole in a tape reader. And again, I determined that by what that particular input was doing, what it was connected to. But I'll go over in more detail in another video exactly how I determined what each hardware function was doing and how they were configured. So that's it for this video. We've so far figured out how the entry point to the program is determined, and also how the interrupt entry point is determined by looking at the 6800 vector table and using the analyzer to confirm what we're looking at, and also to allow us to check that the addresses that we are expecting are correct, and then we can comment the code accordingly. In the next video we'll look at the initialization code to see how the different parts of the machine are initialized, and then after that we'll look at how I determine what each of those ports is controlling and how the zip30 overall code structure is put together. As ever, if you have any questions or want me to cover something in more detail, then drop me a comment.